It's the buildings themselves that are the true wonder.
The greatest mystery about the pyramids is not secret chambers, it's how the Egyptians managed to build them with the technology they had.
For thousands of years, the massive stone monuments of ancient Egypt have stood as silent witnesses to a mystery that has baffled engineers, archaeologists, and historians alike. How did a civilization without power tools, without steel, and without modern machinery cut through some of the hardest stone on Earth with such remarkable precision? The answer, when finally uncovered, revealed an engineering approach so clever that it changed everything we thought we knew about ancient capabilities.
If you do that, you get the kind of accuracy that the Egyptians have achieved when they aligned their pyramids 1/10 of 1 degree. It's a remarkable achievement.
So what exactly made these ancient techniques so puzzling that they sparked centuries of debate? The monuments that defied explanation. When you stand before the Great Pyramid of Giza, you're looking at roughly 2.3 million limestone blocks, each weighing between 2 and 15 tons. The precision with which these blocks fit together is extraordinary. We're talking about joints so tight that you can't slip a piece of paper between them in many places. But limestone was just the beginning. The Egyptians also worked with granite, one of the hardest stones available, cutting and shaping it into massive obelisks, statues, and sarcophagi with surfaces so smooth they almost seem polished by modern machinery. The granite used in many of these structures came from Aswan, located about 500 miles south of Cairo. This particular stone ranks high on the Mohs hardness scale, containing quartz crystals that make it incredibly difficult to cut even with modern tools. Yet somehow, ancient Egyptian workers managed to carve intricate hieroglyphs into it, create perfectly straight edges, and produce pieces that fit together with extraordinary accuracy. Engineers examining these structures kept running into the same problem. The math didn't add up. Traditional assumptions about ancient tools suggested that cutting granite should have been nearly impossible, or at the very least, incredibly inefficient. Copper, the primary metal available to the Egyptians during the Pyramid Age, is softer than granite. In theory, trying to cut granite with copper would be like trying to slice through a steel beam with a butter knife. This apparent impossibility led to wild speculation. Some suggested that the Egyptians must have had access to lost technologies. Others proposed even more outlandish theories involving everything from acoustic levitation to assistance from extraterrestrial visitors. For decades, the academic community struggled to provide a satisfactory explanation that matched both the physical evidence and the technological limitations of the time. The monuments were real, the tool marks were visible, but the mechanism remained frustratingly unclear. The tools they left behind. The first breakthrough in understanding came not from theory, but from physical evidence discovered at ancient sites. Archaeologists working at various locations throughout Egypt uncovered the actual tools used by ancient workers. These weren't mysterious devices or advanced instruments. They were copper saws, chisels, and drilling implements, along with thousands of stone hammers made from dolerite, a particularly hard igneous rock. At first glance, these findings seemed to deepen the mystery rather than solve it. Copper tools were exactly what conventional archaeology had predicted, but they were also what seemed impossible for the job at hand. A copper blade has a hardness of around 3.5 on the Mohs scale, while granite measures between 6 and 7. By all logical reasoning, the copper should have been destroyed long before making any significant cut into the granite. The copper saws found at archaeological sites showed interesting wear patterns. The blades weren't sharp in the traditional sense. Instead, they appeared worn smooth, almost polished by use. This detail would later prove crucial to understanding the actual cutting method. Alongside these tools, archaeologists found something else: evidence of abrasive materials, particularly sand and other minerals, scattered throughout work areas. The dolerite pounders deserve special attention because they reveal part of the solution. These hammerstones, some weighing up to 12 pounds, were clearly used in enormous quantities. At various quarry sites, researchers found literally thousands of them, many broken or worn down through use. The physical evidence showed that ancient workers used these stones to pound away at granite surfaces, a technique that works because dolerite is harder than granite. But pounding alone couldn't explain the precision cuts, the perfectly straight edges, or the smooth surfaces found on finished pieces. Another crucial discovery came from examining tool marks left in stone. When workers abandoned projects, such as the famous unfinished obelisk at Aswan, they left behind a detailed record of their techniques impressed directly into the rock face. These marks showed regular, systematic patterns that suggested organized, methodical work rather than random chipping or breaking. Deep grooves indicated that some kind of sawing action had been used, but the grooves also contained traces of an additional element that would prove essential to solving the puzzle. The real revelation came when researchers analyzed residue found in these ancient cut marks. They discovered particles of quartz sand embedded in the grooves. This wasn't contamination from wind or time. The sand was compressed into the stone itself, pressed there by the cutting process. This physical evidence, combined with the worn appearance of copper tools, started to point toward a solution that was both elegant and surprisingly simple. The quarry secrets. The Aswan quarries provide the most comprehensive evidence of ancient Egyptian stone-cutting techniques. This site contains multiple unfinished projects, including the famous unfinished obelisk, which would have stood over 130 feet tall and weighed approximately 1,200 tons if completed. The obelisk remains attached to the bedrock, abandoned when a crack appeared in the stone during extraction. This failure, unfortunate for the ancient workers, became a gift to modern researchers. Walking around the unfinished obelisk, you can see exactly how the Egyptians approached the task of separating massive stones from the bedrock. The workers created a trench around the desired block, gradually deepening it until they could separate the piece from below. The trenches show clear evidence of the pounding technique using dolerite hammers. Workers would stand in these narrow channels, repeatedly striking the granite surface to pulverize the stone and gradually deepen the cut. The systematic nature of this work is evident in the regular spacing of the hammer marks. Rather than random impacts, the marks form organized patterns that reveal a planned, coordinated effort. Teams of workers must have operated in shifts, each person responsible for a specific section. The efficiency of this system becomes apparent when you consider the scale. Despite the seemingly primitive method, archaeological evidence suggests that skilled workers could remove significant amounts of granite in relatively short periods. But the trenches around the unfinished obelisk also show something else, evidence of sawing. Vertical faces display long, straight grooves that couldn't have been produced by pounding alone. These saw marks run straight and true, maintaining consistent depth and angle over distances of several feet. The precision required for such cuts presents the real puzzle. Even with a copper saw, creating these perfectly straight channels through solid granite should have been nearly impossible. Other features at the quarry sites provide additional clues. Researchers found slots cut into the rock face at various angles, some horizontal, others vertical, and a few diagonal. These test cuts in abandoned works preserve the intermediate stages of the cutting process, showing how workers refined their techniques and adapted to different situations. One particularly revealing feature is the presence of what appear to be guidelines or reference marks carved into the stone, suggesting that the Egyptians used careful planning and measurement throughout the process. The environmental context of these quarries also matters. Aswan sits along the Nile, providing easy access to water for the work sites. Near many cutting areas, archaeologists found evidence of water management systems, including channels and collection basins. The significance of this detail would become clear only when researchers began conducting their own experiments to recreate ancient cutting methods. Modern experiments that changed everything. The real breakthrough came when archaeologists and engineers decided to stop theorizing and start testing. Beginning in the 1980s and continuing through recent decades, researchers conducted systematic experiments using only tools and materials available to ancient Egyptians. The results fundamentally changed our understanding of ancient capabilities. The first successful experiments used copper saws combined with quartz sand as an abrasive. The principle is straightforward but brilliant. The copper blade doesn't actually cut the stone. Instead, it acts as a holder and guide for the sand. As the copper saw moves back and forth, it pulls sand grains across the granite surface. Because quartz sand is harder than granite, these particles do the actual cutting, grinding away tiny amounts of stone with each pass. The copper blade, being softer, allows sand grains to embed partially in its surface, creating a constantly renewed cutting edge of hard, abrasive particles. Early experiments produced promising results but struggled with efficiency. The process worked, but slowly. Then researchers discovered a crucial modification: adding water. Wet sand behaves very differently from dry sand. When moistened, the sand forms a slurry that clings to the copper blade more effectively, maintains better contact with the stone surface, and actually cuts significantly faster than dry sand alone. Some experiments showed that wet sand could increase cutting efficiency by several 100% compared to dry methods. One particularly revealing experiment conducted by researchers at the BBC involved cutting a small limestone block using only copper tools and sand. A team of workers, using a copper saw and continuously adding wet sand to the cut, managed to slice through several inches of limestone in a matter of hours. When they calculated the effort required for larger blocks, the numbers suddenly became reasonable. What seemed impossible for individual workers became entirely practical when you factored in the large workforce and extended timelines available to ancient Egyptian projects. Granite proved more challenging, but the same principle worked. Experiments with granite cutting required more time and more frequent addition of fresh sand, but they succeeded in producing cuts remarkably similar to those found at ancient sites. The tool marks, the width of the cuts, and even the wear patterns on the copper blades matched archaeological evidence. Perhaps most convincingly, these experimental cuts produced the same type of residue found in ancient cuts: quartz particles compressed into the granite surface by the sawing action. Researchers also experimented with drilling, another technique that had puzzled experts. The Egyptians drilled through granite to create sarcophagi, vases, and other objects. Ancient drill cores found at various sites showed spiral grooves that indicated rapid, efficient drilling. Experiments using copper tubes with sand abrasive successfully replicated these results. By rotating a hollow copper tube while continuously adding sand and water, researchers could drill through granite at rates that matched the archaeological evidence. The spiral grooves appeared naturally as sand particles followed the rotating motion of the tube. These experiments also revealed why the ancient methods left such specific tool marks. The consistent width of saw cuts, for example, corresponds to the thickness of copper blades. The depth and spacing of marks made by dolerite pounders match the impact patterns produced by systematic hammering. Every detail that had seemed mysterious suddenly made sense when viewed as the natural result of these techniques applied by skilled workers over extended periods. The engineering genius nobody expected. What these experiments ultimately revealed wasn't just a cutting technique, but an entire system of engineering knowledge that ancient Egyptians had developed and refined over centuries. The copper and sand method represents sophisticated problem solving. Rather than trying to use brute force or impossibly hard tools, Egyptian engineers leveraged material properties in clever ways. They recognized that the abrasive properties of sand could be harnessed and controlled using softer metals as guides. The water component adds another layer of sophistication. Someone, at some point, discovered through experimentation or accident that wet sand worked dramatically better than dry sand. This knowledge was then preserved and passed down through generations of workers. The fact that most quarry sites were located near water sources suggests that this wasn't coincidence, but deliberate planning based on understanding of the technique's requirements. The organizational systems behind these projects were equally impressive. Creating the massive monuments of ancient Egypt required coordination of thousands of workers, management of resources, and maintenance of quality standards across decades of construction. Recent archaeological work has uncovered evidence of worker villages, administrative buildings, and supply systems that supported these projects. The precision of the finished monuments suggests that skilled craftsmen supervised the work, maintaining standards and training new workers in established techniques. Evidence from worker villages near pyramid sites reveals that these weren't slaves toiling under harsh conditions, as often depicted in popular media. Instead, they were skilled workers, many of them specialists in stone cutting, who received food, shelter, and medical care in exchange for their labor. Skeletal remains show that these workers had access to quality nutrition, including meat, and received treatment for work-related injuries. This matters because skilled, motivated workers would naturally develop and refine techniques, seeking more efficient methods and taking pride in quality results. The systematic approach to quarrying and construction also deserves recognition. The Egyptians developed standardized measurements, quality control procedures, and project management techniques that allowed them to coordinate massive undertakings over extended periods. Inscriptions and papyrus records reveal detailed accounting of resources, tracking of worker teams, and planning documents that show sophisticated administrative capabilities. The famous unfinished obelisk was abandoned not because workers couldn't complete it, but because quality standards dictated that a cracked stone wasn't acceptable for such an important monument. This combination of clever technique and systematic organization allowed the Egyptians to accomplish what seemed impossible with the tools available. They didn't need lost technologies or outside assistance. They needed careful observation, willingness to experiment, and the organizational capacity to apply successful techniques at massive scale. That's arguably more impressive than any hypothetical advanced technology. Debunking the wild theories. For decades, the apparent impossibility of ancient Egyptian construction fueled alternative theories that ranged from creative to completely absurd. Claims about laser cutting, acoustic levitation, and extraterrestrial assistance gained popular attention, particularly in television documentaries and fringe publications. Now that we understand the actual methods used, these alternative theories collapse under scrutiny. The laser cutting theory, for example, pointed to the precision and smoothness of some granite surfaces as evidence of advanced technology. Proponents argued that only modern tools could achieve such results, but experimental archaeology proved this wrong. When copper saws with sand abrasive are used with skill and patience, they produce surfaces nearly as smooth as those created by modern tools. Additional polishing with progressively finer abrasives can achieve the mirror-like finishes found on some ancient pieces. No lasers required, just technique and time. Acoustic levitation theories suggested that ancient Egyptians used sound waves to lift and move massive stones. These claims typically ignore basic physics. The acoustic levitation that exists in modern laboratories works only with tiny objects under controlled conditions and requires technology far beyond ancient capabilities. Meanwhile, archaeological evidence clearly shows the ramps, sledges, and roller systems that Egyptians actually used to move heavy stones. We've even found ancient papyrus documents describing these transportation methods. The extraterrestrial assistance theory is perhaps the most frustrating to serious researchers because it fundamentally insults ancient peoples. It assumes that humans of the past couldn't have been as intelligent and capable as modern people. This assumption has no basis in fact. Anatomically modern humans with the same cognitive capabilities as today's population have existed for over 200,000 years. Ancient Egyptians had the same brain capacity, the same ability to observe, experiment, and solve problems. They simply applied these abilities to different challenges than we face today. What these fringe theories consistently ignore is the evidence. We have the tools. We have the quarries with visible tool marks. We have experimental results that replicate ancient achievements using ancient methods. We have records and depictions from the Egyptians themselves describing their techniques. The evidence doesn't point to mysterious technologies. It points to human ingenuity, systematic effort, and accumulated knowledge passed down through generations of skilled workers. The persistence of these alternative theories reveals more about modern biases than about ancient capabilities. We've become so dependent on power tools and machinery that we struggle to imagine accomplishing anything significant without them. Ancient peoples didn't have our tools, but they had time, large workforces, and powerful motivation. They also had something we often underestimate: patience. A project that might take decades didn't seem impossible to a culture that thought in terms of generations and eternal legacy. What this means for ancient history. Understanding how Egyptians cut stone changes our perspective on ancient civilizations more broadly. It demonstrates that we shouldn't underestimate the capabilities of ancient peoples or assume that impressive achievements require lost technologies or outside help. Humans have always been clever problem solvers, capable of remarkable feats when properly motivated and organized. This revelation also highlights the importance of experimental archaeology. For too long, debates about ancient techniques remained theoretical, with experts arguing based on assumptions rather than testing. When researchers finally started conducting hands-on experiments, they solved mysteries that had persisted for centuries. This approach has applications beyond Egypt. Similar experimental methods are now being used to understand ancient construction techniques worldwide, from Stonehenge to Easter Island, often with surprising results. The Egyptian stone-cutting solution also reminds us that simple doesn't mean primitive. The copper saw and sand technique isn't complicated, but it required keen observation of material properties and willingness to experiment with different approaches. Ancient engineers understood practical physics even without modern scientific terminology. They knew that hard materials could cut softer ones, that water changed how materials behaved, and that systematic, organized effort could accomplish seemingly impossible tasks. This knowledge wasn't written in textbooks or preserved in detailed technical manuals. Instead, it was passed down through apprenticeship and practice, from master craftsmen to students over generations. The lack of written technical documentation doesn't indicate lack of knowledge. It reflects a different approach to preserving and transmitting information. Skills were learned through doing, refined through experience, and maintained through continuous practice. The organizational implications are equally significant. Managing projects on the scale of the pyramids or massive obelisks required sophisticated administrative systems. The Egyptians developed bureaucratic structures, record-keeping methods, and project management techniques that wouldn't be out of place in modern construction projects. This administrative sophistication supported and enabled the technical achievements, showing that ancient civilizations could be complex, organized societies capable of long-term planning and execution. Perhaps most importantly, solving the stone-cutting mystery restores credit where it belongs. The ancient Egyptians deserve recognition for their actual achievements, not imaginary ones. They built incredible monuments through intelligence, organization, skill, and sustained effort. That's the real story, and it's far more inspiring than tales of lost technologies or alien assistance. It tells us that humans, working together with determination and clever techniques, can accomplish extraordinary things even with simple tools. That's a lesson worth remembering. The massive stones of ancient Egypt no longer need to puzzle us. The mystery that seemed impenetrable for so long yielded to careful investigation, experimental testing, and willingness to take ancient peoples seriously as capable engineers. The tools were simple, the materials were basic, but the thinking behind their use was brilliant. Sometimes the most profound discoveries aren't about finding something new, but finally understanding what was there all along.